Welcome. Today we are going to discuss few things which is of tutorial type. Not much new concepts would be discussed today. However, some results which are nice and useful would be shown today about the resolvent operator. Okay, so we start from here. So here I'm first showing another expression of the resolvent operator. So let A be the infinitesimal generator of a C0 semigroup TT. Consider the following operator R, okay, where R is an operator on that one Banach space, okay, on which the TT is the bound linear operator, is the semigroup bound linear operators. Okay, this R is an operator which is defined in this way: R applied on X, small x is a member in the Banach space capital X. Okay, so R applied on X is defined as integration 0 to infinity e to the power minus lambda t, capital T of Tx dt. Okay, so and this integration t running from 0 to infinity. Okay, so here which lambda is it? So lambda is some positive real number. Okay, so this is something very familiar expression. We have seen this such expression in some other courses or in some bachelor degree courses. So this integration is called Laplace transformation. Okay, so this is Laplace transformation of this function. So now if you consider this as a Banach space valued function of time t, and then this R is a Laplace transformation of that. So ttx takes value in the Banach space capital X. Okay, for every x, small x, you get this integration. However, the question arises, why should this integration exist? Okay, so this exists for sufficiently large lambda. Why is it so? Because we have seen when we consider a C0 semigroup capital T, then we have studied the growth property of capital T, correct? So there is one lecture dedicated to that. So in that, what we have seen that norm of TT that can be upper bounded by one exponential function. Okay, so we have written in the following manner that capital M times e to the power of omega t. Okay, so now so far norm is concerned here. So norm wise, this can be upper bounded by m times e to the power of omega t. And if lambda is larger than omega, then integrand, after taking the norm, okay, so this norm of this integrand would be upper bounded by one constant, okay, and not only constant, that would decay, right? If lambda is more than omega, that would decay to 0, okay, so exponential decay that would have, and hence this integration would be finite. Okay, so this that means this so for sufficient large lambda, so that lambda more than omega, so then this integration is finite. Okay, so this is well defined in the strong sense, okay, in the absolute sense. Okay, so indeed, for lambda more than omega, the integral exists with finite norm, so norm would be finite. So what does it imply? That implies that R would have finite norm. Okay, so R would be, and then you can ask that whether the operator norm of R is finite or not. So of course you can take x on the unit sphere of the Banach space and take supremum of that. But whatever norm x you take, norm is equal to 1 you take, you know that is upper bounded by capital M times e to the power of something which goes to 0. So that would be finite. So this immediately implies that R has finite operator norm. So So from here we can conclude that this operator R defined in this way, the Laplace transformation of tt, is a boundary linear operator. Why linear? Because linear is very clear because it is acted linearly from here. Okay, so now onward we fix lambda, which is more than omega, correct? We fix lambda more than omega. So hence this implies that R is a boundary linear operator on X. Now what we do is that we would try to find out whether this R is in the domain of definition of the generator of tt. Okay, so that we are going to check, and then we are going to check whether this R can be identified as the resolvent operator. Okay, so we would come to that point later. So first we check this. So to check whether R is in the domain of the definition, Rx is in the domain of the definition of generator, what do we need to do? We need to take this fraction th minus identity by h and let h tends to 0. Okay, and if that limit exists, then we can say that the range of R is in the domain of operator A, where A is the generator of tt. Okay, so we do this. So we take h positive and then we take this fraction th minus identity divided by h times R, operated on Rx. Now this thing we are writing down here. So 1 over h I write down here, and then th and then R, okay, th composition R, so that if I put th here, thr, th here, so I would get capital T of h plus t here, okay, and then so e to the minus lambda t, capital T of t plus h x. Okay, so that we are going to get, and then identity map is there, so minus R, so it is exactly the same. So it is e to the minus lambda t tx, e to the minus lambda t ttx. This is coming from this I, identity operator, okay, and 1 over h is outside. So this expression, left hand side expression, is written on the right hand side. Now what we do is the following. What we do, we write down using some substitution of variable. So instead of lambda t, if I write down lambda t plus h, okay, then I have to subtract also h, t plus h minus h, okay, that way. So lambda t plus h, if you do, and then we replace t plus h as t, okay, so then instead of it would start from 0, it would start from h to infinity, okay. So instead of starting h to infinity, if I write down 0 to infinity, okay, so then I have to add some 0 to h, okay. So that thing we do here. So here we add here h and then minus h, minus sign, plus sign, so plus e to the lambda h we take here. So e to the lambda h, if we do, then it is like e to the lambda t plus h and then t plus h here, but then h to infinity, but then again using the substitutional variable, so we want to write down this as 0 to infinity, and then some term would be required, so 0 to h term would be required, so we write down 0 to h, okay, 0 to h e to the minus lambda t ttx dt. So for this term we do, and then the minus 1 term, where is it coming from? It is coming from exactly this, okay, e to the minus lambda t ttx dt, 0 to infinity. So this is exactly that, e to the minus lambda t to ttx dt, 0 to infinity. Okay, so this minus 1 term is coming from here, and then just to manage this term, I had to take something common here, and then something I need to subtract something here. Okay, so this is a very convenient expression on the right hand side what we have obtained. Why is it so? Because now I can take, this integration is independent of h, only this term, and for this we can take limit h tends to 0. We know that limit exists. Why? Because e to the power lambda h minus 1 divided by h, I can write down as lambda h and lambda here. So then it is like e to the power x minus 1 divided by x form, okay? And as limit x tends to 0, that goes to 1. We know that. So what would be the result of the limit of this? That would be just lambda. So lambda would be the limit of this expression, and then this would remain as it is. And for this, I have e to the power lambda h. So this numerator as h tends to 0 goes to 1. And then this 1 over h, and then this integration as h tends to 0, it converges to the integrand where it is evaluated t is equal to 0. Okay, so because this is in the neighborhood of 0, correct? It is like a derivative of the antiderivative, correct? So it's the same thing. Okay, so here, from here we are going to get e to the power of minus 0, that is 1, t0, this identity x. So this would give me just minus x actually. Okay, so as h tends to 0, that right hand side converges, hence left hand side is in the domain of A, and then left hand side, is this thing would converge to capital A. So ARX. So ARX is equal to lambda times Rx minus x. Why? Because this is going to give me lambda, as I have mentioned, this is going to give me x, and then this inside thing is, from definition, is Rx. Okay, so right hand side is becoming lambda times Rx minus x. So this is true for all possible x, small x, correct? So we can conclude that the operator AR is equal to lambda minus identity. Okay, so now if we wish to take R common from these things, so I take lambda on the left hand side. Okay, so then this lambda I minus A times R is equal to identity, and then cancel negative sign, we get this expression. Okay, so what does it imply? It implies that R appears like a right inverse of lambda minus A. Okay, so recall the definition of resolvent operator. Resolvent operator was the inverse of lambda minus A. Okay, so this is an indication that but we need to show that is also the right inverse. Okay, so for that, what we need to show that A and R commute each other. Okay, A and R commute each other, but for that because A is not defined on the whole domain, correct? So one has to be careful that what is the meaning of commuting each other. So when small x is in the domain of A, for that AR is same as RA. Okay, so in that sense. Okay, so here we go again for x in the domain of A, Rax equal to integration 0 to infinity e to the power of minus lambda t tt ax tt. Okay, how did we get it? Because just from the definition, if Rx, just R applied on Ax, so I have written Ax here. Now we know that TT and A, they commute each other. So TTA is same as ATT, okay? And then this whole thing, so TTX and then integration 0 to infinity, this thing is in the domain of A. So A comes out here. So A operating on 0 to infinity e to the power minus lambda t ttx tt, and this whole thing is Rx, so is equal to Arx. So this clarifies that R and A commute, so as long as small x in the domain of A. Okay, so hence R commutes with A. So here also you can do the commuting things, and we can conclude that R is equal to lambda I minus A inverse. Okay. So this proves that the resolvent operator, which was given as lambda I minus A inverse, okay, so that has another alternative expression, and that expression happens to be very interesting. That is just nothing but the Laplace transformation of the semi-group, okay. And here, only thing is that where you talk about when it exists, correct? When lambda is more than omega, then it exists, okay, for that reason. Okay, and that is also is not a additional assumption, because to define R resolvent, you also need lambda I minus A is invertible in the first place. So that means you need lambda to come from the set of resolvent set, correct? So this is basically equivalent condition. There is no additional condition for this expression. And for this reason, actually, in many authors take this as a definition of the resolvent operator. Okay, unlike us, I mean, we have taken lambda I minus A inverse as the definition of resolvent operator. Okay. Okay, now we go to next topic,